Okay, let's dive right into this explainer. Today we're taking a look at a topic that, honestly, a lot of people just write off as a mundane IT checkbox. But as we're going to see, it's actually a high-stakes, billion-dollar forensic investigation: software testing. Software literally runs our world, and based on the source material we're unpacking today, testing isn't just about making sure a Buy Now button clicks correctly. It's about preventing catastrophic financial ruin and, quite frankly, protecting human lives.
Here's our roadmap for today. We're going to start with the historical catastrophes of the lasting software crisis, break down the anatomy of a bug, look at the true aims of testing, and then finally open up the detective's toolkit to examine both static and dynamic testing techniques.
So, Section 1, the lasting software crisis. You know, ever since the 1960s, raw computational power and software complexity have ruthlessly outpaced our methods to control them. Computer scientist Edgar W. Dijkstra actually coined the term software crisis way back in 1972. We're basically building massive systems faster than we can invent ways to ensure they actually work.
To put that into perspective, take a second to let this number sink in. $1.6 billion. That is the minimum estimated amount lost during a catastrophic software modernization failure by the U.S. Internal Revenue Service. The project was delayed by 8 years and just hemorrhaged taxpayer money. It brilliantly illustrates that testing is absolutely vital. A failure at this scale isn't a technical glitch. It's a massive economic disaster.
And it doesn't stop at financial systems. These failures literally extend into space. Back in September 1999, NASA lost the Mars Climate Orbiter. Why? Because a supplier, Lockheed Martin, used imperial units instead of the metric system. The software didn't convert the data. So instead of orbiting at a safe altitude of 150 kilometers, the spacecraft dipped down to 57 kilometers and was just utterly destroyed by atmospheric friction. A simple, untested unit mix-up completely annihilated an entire space mission.
Moving into Section 2, anatomy of a bug. So, how do these massive failures actually happen at the code level? Now, in everyday language, we call everything a bug. But in the rigorous world of software testing, bug is just a casual umbrella term. The true vocabulary here describes a very precise chain of events.
It's like a domino effect. It all starts with phase 1, a human error. Maybe a programmer gets tired, misunderstands a spec, or just types the wrong number. That human mistake creates phase 2, a defect. A defect is a static flaw sitting silently in the source code. It's just waiting there. Finally, we reach phase 3, a failure. A failure only happens dynamically when the program is actually executed and the system hits that defective piece of code to produce a bad result. So human error creates a static defect which triggers a dynamic failure.
But wait, there's one more piece to this puzzle: an incident. An incident is any condition that violates a program's specification. But here's the catch: not all incidents are failures caused by bad code. Sometimes it's just the testing environment acting up, or maybe the tester doesn't have the right system permissions. Those are external glitches. A good software detective has to separate true failures from mere incidents so they don't send developers on a wild goose chase.
All right, Section 3, the aims of testing. Now that we know what we're looking for, why do we put software through the ringer? We're zooming out from code-level fixes to the massive organizational impact this has.
I absolutely love this quote from our source material. To test a program is to try to make it fail. It's charmingly simple but profoundly true. You see, testing isn't about gently verifying that a program works perfectly under ideal conditions. No way. It is an aggressive, active, hostile search for failure. You are essentially trying to break the system before the real world gets a chance to. Beyond just breaking things for fun, finding these failures serves crucial economic goals. Testing helps us assess overall quality and, crucially, decrease defect removal costs. I mean, it is so much cheaper to fix a defect in the lab than after you've shipped it to millions of users, right? Plus, it helps companies avoid massive lawsuits, builds user trust, and gives developers the exact data they need to support effective debugging.
But this highlights a really stark dichotomy. On one hand, testing is an economic obligation, saving money, preventing budget overruns. But on the other hand, it's a severe ethical obligation. The source highlights a truly tragic incident from October 1992 involving the London Ambulance Service. A brand new computer-aided dispatch system failed, delaying emergency calls. That technical disaster was attributed to up to 30 fatalities. So testing isn't just about dollars and cents, it is literally about preventing harm to human beings.
With those incredibly high stakes in mind, let's open up the toolkit.
Section 4, Static Testing Techniques. This is where we hunt for clues without actually running the program. Imagine a detective examining a crime scene without touching a single thing. That's static testing.
Broadly speaking, static testing falls into two buckets. On the one side, we have verification. This is a highly formal, rigorous mathematical process of theoretically proving a program matches its exact spec. It takes immense effort, so it's mostly reserved for ultra-critical systems. Think nuclear power plant controls or the Paris Metro. On the other side, we have static analysis. This is a much more practical, highly automated approach where tools quickly scan the source code looking for anomalies.
So, what does static analysis look like day to day? Well, we have style analysis to make sure developers are following programming conventions, slicing to discover how different statements relate to one another, control flow analysis to find dead code that can't ever logically execute, data flow analysis to detect weird anomalies, like defining a variable but never actually reading it, and of course, good old-fashioned code reviews, where human eyes inspect the code. Just remember, these static methods generally provide strong hints of defects rather than exposing the actual dynamic failures.
To expose those actual failures, we have to flip the switch. Section 5, Dynamic Testing Techniques. This is the crucial phase where the code is actually executed, fed with data, and pushed to see exactly where and how it breaks. We can neatly separate the two main philosophies here. First, structure-oriented testing. This is a glass box approach. The tester looks directly into the code's inner workings, trying to cover every single path and branch. Second, we have function-oriented testing. This is a black box approach. The tester doesn't look at the code at all. They just look at the spec and test the inputs and outputs based on what the software is actually supposed to do.
A perfect concrete example of this functional approach is equivalence partitioning. Imagine you have a text box that accepts the hours in a day. Testing every single number in the universe is literally impossible, so you partition them. Step 1, identify your valid class, which is 0 through 23. Step 2, identify your invalid classes, like -1 or 28. Step 3, just pick one representative value from each group to test. It's brilliant. Grouping inputs like this avoids an impossible workload while still rigorously challenging the system.
But functional correctness is really only half the battle. We have to ask a pivotal question. What happens when software faces impossible demands? To test limits, we use two very distinct methods. A load test assesses how the system behaves under a typical expected workload, like making sure an e-commerce site can handle normal holiday traffic. A stress test, however, throws an extraordinary, totally impossible load at the system. The absolutely crucial point here is that we know the system will break during a stress test. But when it breaks, we're looking for graceful degradation. We want the system to safely save data and drop new requests, instead of suffering an abrupt, catastrophic crash that corrupts the whole database.
Now, as testing evolves, researchers are getting incredibly clever. Enter dynamic symbolic execution. Instead of testing with constant numbers, this method executes code treating variables as mathematical logic expressions. It automatically maps out exact paths to failure. The source material highlights an advanced research tool called Muggle that uses this hybrid approach. It acts like an automated super detective, generating incredibly precise test cases to hunt down complex flaws.
But, despite all this math, all the automation, and symbolic execution, sometimes you really just need a human. Experience-based testing relies entirely on a veteran tester's intuition. It's called error guessing. They just develop a sixth sense for where a programmer might have messed up. They perform exploratory attacks on the software, uncovering deeply hidden flaws that no automated tool would ever even think to check.
And that human element brings us right back to why we do this in the first place. I want to leave you with this stark reminder from our source. System failure has a serious impact on society. Preventing software from harming humans is an ethical obligation. Testing isn't just some frustrating delay before a product launch. It is an ethical shield protecting our finances, our privacy, and in some cases, our very lives.
We've covered some incredible ground in today's explainer, from the anatomy of a bug to the outer limits of stress testing. But I want to end with a provocative thought for you to take back to your own projects. As software complexity continues to scale exponentially faster than our methods to handle it, is your code actually safe, or is it just quietly waiting to fail? Something to think about next time you go to deploy. Thanks for joining me, and keep questioning the code.